Hello students, so today in this lecture, this is a continuation of our previous lectures on transport phenomena. So in this lecture, we will mainly focus on surface tension. Now before starting surface tension, we need to understand what is meant by this term, continuum assumption. Now by continuum assumption, uh, it means that we are treating the fluid as a continuous medium, fluid as a continuous and homogeneous matter. So it's first it is continuous, and secondly it is homogeneous. And by these assumptions, what we basically mean is that we are ignoring the discrete nature of the molecules involved. Ignoring the discrete we are basically ignoring the discrete nature of the molecules. Ignoring the discrete nature of the molecules. Now, there is a certain scale up to which we can do it. By scale, we mean that what is the dimension of the pipe through which it is passing. That means if the dimensions of the pipe is such that it is much larger than molecular dimensions, that means the pipe, the length of the pipe is such that this length of the pipe is much greater than the mean free path of the molecules. By mean free path, we mean the distance traveled by a molecule before it coincides or it is in contact with another molecule of its same kind or different kind. So this is what is meant by scale. So as long the scale is large, we can treat the liquid to be a continuous as well as a homogeneous. Okay, so this is the first assumptions that we make in fluid mechanics. Okay. Now, there are certain parameters on which the fluid properties are based on. We have already discussed. So, first is your density, velocity, temperature, velocity, temperature, and pressure. And so these functions are also they are treated as continuous functions. Continuous functions of space and time. Let's not put it x because let's call it as space and time. So by space we mean both x, y, all the three directions, y and z directions. So this is one another aspect. Secondly, we have discussed the concept of viscosity, and by viscosity we mean the internal friction between the different layers of liquid. Now there is so the viscosity that we know of, where tau, the shear force, is proportional to viscosity into uh, dv by dx. Now this viscosity is called the dynamic viscosity. This is called the dynamic viscosity. Now, if we again uh, divide this dynamic viscosity by density, we get another quantity. Let's call it as nu. This is called the kinematic viscosity. Kinematic viscosity. So let us one is the dynamic viscosity, another one is kinematic viscosity. So these are again functions which are continuous functions. Okay. So this is the preliminary concepts before going into the main topic of today's discussion, that is the surface tension. Okay. Now, what is the surface tension? Surface tension is basically, if we define the surface tension in very simple term, it is the force or it rather it leads to the force between the interface between two fluids. Interface between the two fluids, and the reason of its occurrence is mainly considered to be the cohesive force in the fluid. Now, now let us take an example that if we have a ring and somehow you have a film of any liquid material like soap, and you allow this material to vary over the time, you will see that the soap film, it actually contracts. You can see this example in the formation of bubbles, the bubble formation device. You have a ring like this, you have a soap film, and you blow air in it, and so different bubbles are formed. And if you keep the ring with the soap film for a certain amount of time, and you allow you burst the film, then you see that there is a contraction of the film and it goes towards one of the ends. So that means a force is acting to make the on the surface of the film. Okay. So what we can infer from this observation is the liquid surface is behaving like a stretched membrane. You can see that the liquid surface is behaving like a stretched membrane. Okay. And due to this stretched membrane, this has a tendency to contract. Now, since it is contracting, like as we have seen in the case of the soap film, there is a contraction taking place. So it means that there exists a tangential force which makes the films to contract. So this tangential force per unit length, let's call it as F. This tangential force per unit length is actually what we know as the surface tension. Now we have another parameter which is known as surface energy. Let's call it as E. Now a force is present, force per unit length, which we have called as the surface tension. Now if a liquid surface exists, there's in any existence of liquid surface, it means that a work has been done against the existing force. That means a surface has been produced in presence of this force. So therefore work must have been done. So surface produced in presence of force F. So it means that work has been done. Work has been done, and so this work done remains stored in the surface as its potential energy, and so this potential energy is nothing but the surface energy. So we can put it in this way. We can see that the work done per unit area means E per unit area of the surface. We're calling it as the surface energy density. In fact, the E is not the E's as we have discussed here. This is actually the surface energy density, not the surface energy alone. And it can be also seen that the surface energy, the surface tension is equal to the surface energy density at T is equal to 0. So this is the basic concept. So in terms of units or dimensions, the surface tension is force per unit area, that is Newton per meter. So if you represent it in terms of tension, Newton is a mass into acceleration, L T minus 2, whereas the surface energy E is Newton meter per meter square. So it is also equal to Newton per meter, and is having the same dimension as the surface tension. Now let us come to some of the observations that are found which can be related to surface tension. The first observation that we see is shape of drops. Now if you put a drop on a surface, very small drop, you see that the drop is spherical in nature. The reason of occurrence of this spherical nature of drop is the total potential energy associated with this drop, total PE, is a combination of two terms. First of all, this drop has got a mass and it is at a height h from the surface, so that gives it the usual potential energy mgh. And the another contribution comes from the surface tension, that is surface tension multiplied by, now this h is the center of gravity, height of the center of gravity. Another one, the surface tension plus multiplied by the surface area, AS. So these two combine to form the total potential energy of the liquid drop. Now if the drop is very small, so this H, so for small drops, this the height of the center of gravity, it gets neglected, tends to 0, and the main contribution comes from only the surface tension of the drop. However, if the size of the drop increases, larger drop, then the mgh part becomes more dominant. Okay. Now the reason why it assumes a spherical shape is that in nature every system tries to be in its lowest energy state. So if when the drop is small, and when that means when the contribution is only coming from the surface tension multiplied by the surface area, to go into the minimum state, this surface area needs to be minimized. The lower is the surface area, the lower will be the total potential energy, and in doing that, the lowest possible surface area for a particular volume is the spherical surface area. So that is why it assumes a spherical shape. Now, the second case is when you have two different fluids. So this is the first fluid, which is of a higher surface area, higher dimension, and above which very small fluid has been placed. So the first fluid is having, say, let's call the first fluid as A, and the second fluid as B. And there is also an interface existing between the first and the second fluid. Let's call that as AB. So what we can imply from this is we now have three different areas. One is the surface area of the primary fluid, or the larger one, surface area of the smaller radius fluid, and there is an interface area as well. So there are three different surface areas. So now this B, it is expected to spread over A, and let's say it starts to spread, it starts to increase in size. So increase in size is, say, dA due to the spread. So as dA increases, so there will be an increase in potential energy as well, the dE, and that dE will be equal to the surface area, or sorry, the surface tension. These are not surface area, these are surface tensions. Surface tensions, not surface area, sorry. So it will be surface area of B plus surface area of AB minus the surface area of A multiplied by the change in area that has taken place in B as it has grown in size. Now, if the surface tension of A is greater than SB, surface tension of B, and surface tension of the joint region, interface region, then dE will be negative. D will be negative. So the spreading will now cause a decrease in area, decrease in energy. There will be a change in energy will be in the lower side, and in the opposite case, when the surface area of the first fluid is less than the wetting fluid and the surface tension of the interface region, in this case dE will be positive, but it will increase with an increase in dE. Okay. So whether a fluid will spread or not again will depend upon the surface tensions of the different liquids in the system. Now the triangle, now these three values SA, SB and SAAB, they actually form a triangle. To one side you have SA, one side you have SB, and you have SAB. You can form a triangle like this. And so Now this triangle here, it is an isosceles triangle with all the three values 60 degree, but this is usually not the case. Depending upon the values of the surface tension, the triangle may change the angle. For example, if the SA is larger than SA and SB combined, it will be like this. So there will be a certain angle associated with this. If on the other hand, if it is smaller than SA and SB combined, then again it will be there will be another angle associated with this. So this value, this will keep on changing, right? For larger A, this side will keep on changing. So there will be a change in angle associated with the different values of the surface tension. Now this brings us to the next concept of liquid solid contact. Okay, now previously this triangle, it has got a name. The triangle formed by SA and SB and SC, it is called Newman's triangle. So Newman's triangle. Okay. Now going back to our main discussion. So the next topic is the liquid solid interface, and or in other words, what is known as the contact angle. Now you might have seen that if you put a liquid in a vessel, the liquid may take shape like this, or it may take a shape like this. Ordinary liquids usually have a shape like this, and liquids which are a little bit thicker, they actually form a convex shape. So this is for ordinary liquid, whereas this one is for liquids like mercury, Hg. Now, so the angle which is created at the interface, this angle, or rather this angle, these are called contact angles. So here the contact angle theta is less than 90 degrees, whereas in this case it is more than 90 degrees. Contact angle or angle of contact. Okay. Now, what causes this curvature? That needs to be first answered. So, for that we need to just look into the interface once again. Say, so there is a molecule at the liquid solid interface. There's LS region. So let's say this is LS region. And when there is a molecule, there are three different forces existing due to this molecule. First one is the weight of the molecule itself. Number one is the weight of the molecule itself due to the mass. So let's call this one as M. So if we take the case of the ordinary fluid, this is where the mass will act. vertically downwards. Okay, there is another force due to the adhesion between the liquid and the solid. We call this one as the adhesive force N. So this adhesive force usually acts perpendicular to the weight. And again we have the third force due to the cohesion of the molecules. Let's call that one as R. So the cohesive force again acts in this way. So we have N, we have M, and we have R. Now the resultant of these three forces will also act in certain direction. So in this case, since the adhesive force is dominant here, so the resultant will be in this direction. Let's call this one as the O. So for ordinary liquids, the resultant force has a direction like this. However, in the case of those liquids where a concave meniscus is formed, the reaction, the cohesive force is much higher, since the liquid is usually thick. It is much higher than the adhesive force. So this makes the resultant force in this direction, O. Okay. So this causes the contact angle to vary from liquid to liquid. Now, what about the surface? If you look at the normal surface, the surface has no mass, so we will put the M. The surface will not have any reaction, any adhesive force, so we will put N going towards 0. So decrease in mass usually will also cause a decrease in the resultant force, decrease in the reaction force, the cohesive force, and this will again cause this resultant force to go down, so ultimately it becomes horizontal. So this makes the surface region to be a horizontal region. Okay, that means when a liquid is falling onto the surface, it tends to follow this horizontal region. That's why it spreads. But if you put in a vessel where the surface is rather in a perpendicular direction, so here it actually forms a meniscus, either a concave or a convex. So this is for today's lecture. We will continue the different aspects of surface tension in our next class.